Okay, big thanks to all of our speakers. It is my distinct pleasure now to introduce our first keynote speaker. This is Raquel Urtasun. She's the founder and CEO of Waabi, an AI company building the next generation of self-driving technology. She is also a full professor at the University of Toronto, Department of Computer Science. She's also a co-founder of the Vector Institute for AI and the recipient of several high-profile awards, including the Longuet-Higgins Prize, an Everingham Prize, an NSERC EWR Stacy Award, 2 NVIDIA Pioneers of AI Awards, 3 Google Faculty Research Awards, an Amazon Faculty Award, and many more. She has also been recognized as 100 Women of Impact of Entrepreneur Magazine, 100 People Transforming Business by Business Insider, and Toronto's most influential Torontoans, according to Toronto Life magazine. Without further ado, I'll let her get set up, and let's all please welcome Raquel Erdeson.
Hear me? Yes, no. Yeah, I was saying thank you for the kind introduction. Sorry, we have a slightly complex setting here. So give us 2 seconds. Amazing. I have to say that these guys are amazing. So thank you for all the support for getting the, I guess, AV, which is always not autonomous vehicles, but in terms of presentations, which are always difficult to get right. Anyways, it's a pleasure to be here today, and thank you for the organizers to inviting me. It's always great to come to robotics conferences, which I don't have the pleasure to go very often. So today I'm going to be talking about what I think is the next way to go over trying to solve self-driving at the scale, which is with an AI-first approach, which I think that most of the audience will agree with me, that it's time for a modern approach to self-driving vehicles. So I think it's important to know that the promise of self-driving has been made for many years, but remains extremely exciting because once they are there at the scale, they are really going to transform the world as we know it today. It's going to be much greener in terms of the cities that we're going to have. We are not going to have supply chain issues, and there is going to be enhanced safety to our roads. And I really look forward to see them everywhere. Now it's going to take a little bit more time to get us there. And today I will be talking a bit about the technology that I believe will get us there. All right, so just to maybe a little summary of what we are doing at Waabi and what Waabi is. So a year and a half ago, almost a year and a half ago, I founded a company called Waabi, which the idea is to really bring the next generation of self-driving technology to the market. And it's a company that is not focused on showing flashy demo. It's a company that is really focused into bringing this technology to everyone out there. We are based in Toronto as well as San Francisco. We have a whole bunch of remote people as well. And in order to bring this vision to life, I fundraise, I guess, a whole bunch of money, $83 million, on the first day of opening the company, which was, I think, the largest Series A in Canada. We have a highly differentiated approach. Today I'm going to be talking a bit about what that means and what it is. And there is a lot of really, really exciting stuff happening in the company where, as I said, we are laser focused now in logistics, bringing self-driving transportation to our highways, really transporting goods, right? These days it's really hard to get anything out there because of the supply chain issues, and it's getting worse and worse because there are not enough drivers. So automation is the only way to get there, and that's what we're trying to really solve with Waabi. All right, so enough about the company. Now let's get into the technical stuff. So for all of you, just to get on the same page, let's talk a little bit about my 30 seconds introduction to self-driving. Okay, so bear with me. This is probably obvious for everybody here. So in terms of how every self-driving vehicle typically works out there is that you capture information from the sensors. I'm showing this with the LiDAR point cloud seen from the top. Typically, almost all we use high-definition maps, which are these beautiful maps that give you a lot of information about the environment before you even see it. So the first task is really to localize the vehicle so that you can employ these high-definition maps as a prior for your autonomy stack. Once you localize, then the idea is that the perception system is going to be looking around and seeing all the different objects that appear in the scene. And then you need to predict how these objects are going to be moving and what they're going to be doing in the next few seconds. And this is key because in order to plan a safe maneuver, you need to understand the intention, what's going to happen in the future. Otherwise, you will have very aggressive plan or very reactive that will be unsafe. Okay, so prediction is a very, very important key component of self-driving, and it's a pretty hard task. Then, given the information about the past, the present, and the future, you need to reason about what you should do as a self-driving vehicle, and basically every fraction of a second plan what your maneuver should be, right? And typically you repeat this process every 100 milliseconds or so. Okay, this is in a nutshell how almost every self-driving vehicle works. Now, if we look a little bit out there, right, so the industry has made, I would say, significant progress, but the promise of self-driving vehicles everywhere is really far from being fulfilled, right? If you live in San Francisco, you can see quite a few. If you live in any other city, you see none, right? So there is, a couple of reasons why this is the case. One of it is that, the industry has been pretty bad at basically stating the obvious, which is that this is a very, very hard problem to solve. Right? We need, the collective minds of people like you in order to really bring this technology, right? In order to really develop and invent this technology, right? So why is it hard to do driving or self-driving? Is that the decision process is actually pretty nuanced. Small changes in the environment fully change your reaction, what your maneuver should be. Also, the number of possibilities is extremely large. There is exponentially many things that you're going to be exposed to, and most of them are actually really rare. So typically, you're going to need to drive millions, billions, trillions of miles in order to see one of these events. So that makes it a very, very hard development process. But it's not just about the problem being hard. It's also that the technology is far from being, perfect or the right technology to solve this. Right? There has been a lot of consolidation since the DARPA challenge. Typically, what you see in the industry is that every software stack is almost a copycat of, the stack that you see somewhere else. And this comes because it is a cross-pollination of people and ideas in the industry. And this is good if you have solved the problem. This is actually really dangerous if you haven't solved the problem, because you have the collective power of the world thinking the same. And this is not the way that you come up with what is the best solution out there, right? As researchers, what do we know is that we need to look at many different ways to solve the problem in order to advance science, in order to advance this difficult problem. All right, and in terms of why do I say that the technology is far from perfect is because they use a very hand-engineered approach where all over the process requires humans. And that's actually really costly. That's something that is very difficult to generalize. And if you look at the software stacks, they still look very similar to what you observed during the DARPA challenge, which is almost 20 years ago now. Right? 20 years is a lot of time. Let me give you a little bit more details about, what is it that, we don't like about the traditional kind of hand-engineer approach to solve self-driving. So typically, as I mentioned before, is this modular approach where you have, a set of blocks here, perception, prediction, planning, etc. Right? But when you go, deep in the weeds into how these technologies develop, there is no holistic thinking. Instead, you typically have, thousands of people, right, working on this problem, and the pie gets split into sub-problems that get split into smaller sub-problems, and then an engineer or a researcher working on self-driving will end up working on these very small parts of the problem. For example, I want to track pedestrians that are crossing the street jaywalking. Right? So it's very hard to actually build the right thing if you're thinking of this very, very small problem. And then somehow you need to piece together all this stuff to make the right decision making. Right? So it's going to be hard to solve it that way. Also, this is a software stack typically that is built by humans for humans. Right? What do I mean by this is that interfaces between the different modules are very, very small. Typically, you will see things like the state of the different actors, maybe some notion of uncertainty, but if you made a mistake, it's impossible to correct. So you end up with this cascading of mistakes along the stack. Furthermore, the other thing that you will see in the industry is that typically you go on the road and then you drive and drive and drive, and then you typically see, you categorize the type of mistakes that your system does. Let's say that your system gets fooled by, leaves on the ground, then you end up, spinning up an effort to actually try to solve that problem. And yet you add one more module to this complicated software stack. So you end up with this spaghetti code that is really, really hard to make it to work. And finally, there is no automation. Every time that you make a change, you have to retune the entire system. And this is, hundreds of modules, right? So it turns out that in industry, if you make a change, it takes you 1 quarter, 2 quarters to land that change, right? And this is why it's very, very hard to make progress. So we need something different, right? We need to go from this very human-centric approach to something that is better for machines. So, I'm going to be talking about an AI-first approach, and I'm sure that the first thing that everybody is thinking is something that looks like this, right? Is that Raquel is advocating for this black box neural net that is going to solve everything. Well, not really, right? So if you just go and think that a single neural net is going to solve your entire problem, it's going to be hard for you to get there because there is no interpretability. If the system makes a mistake and you need to explain to the regulators why you made a mistake, you're going to be in trouble, right? So this is not something that you can really put on a product out on the road. And if you think about a neural network like this that has to generalize to all the possibilities of the environment, you need to expose it to so many examples, right? Including all the safety critical cases, including all the accidents so that at least it slows down or does the right thing in order to minimize impact. And there is no way that you can do that. That's not ethical, right? So we need something else. So what we are building and what I've been advocating for the past, I don't know how many years now, is to do something that is the best of both worlds. And the idea is that you're going to have still the modularity, you have the interpretability of the interpretable representations, but at the same time, you use automation. You have the ability to train the system end-to-end. Okay, end-to-end doesn't mean black box neural net. And this is a misconception that has been out for many, many years. You can still have a modular approach, an interpretable approach, and have the ability to train the entire system. Okay? And this is a very, very powerful concept. All right, so the kind of technology that we are building is AI first in the sense that it's end-to-end trainable, so you get the automation. You have these more complex interfaces so that you can propagate uncertainty much better. All the way to motion planning and control, you can get access to the raw sensor data so that you don't have this cascade of mistakes, and it's very scalable, very affordable. You can develop this with much less people, whatever the word is in English, as well as it generalizes really well. And in particular, we use a new generation of AI algorithms that use probabilistic inference, complex optimization, and deep learning. Okay? Yes, utilizing AI as we know it today is not going to solve the problem either. Okay? So you need to innovate. There is a need for research. All right, and the last bit that we need is also we need a high, real-world, high-fidelity closed-loop simulator. That's the other key component that in order to solve this task. Okay, this is something that has been underestimated in the industry, and that with Waabi will really bring it to the front page into this is a tool that you need for development, for validation, for verification, for the safety case. And I'm going to show you today Waabi Wall, which is our answer to simulation. All right, so the agenda of today is I'm going to first be talking about autonomy. And I have some bad news, which is I'm not going to show you all the new stuff we are doing at Waabi in the autonomy front. Okay, we haven't yet made public, so you will need to wait a couple more months, but I promise you that we are going to showcase it at some point. So I'm going to be just building you a story in some of the work that we have done over the past 5 years or so. Okay, and then I'm going to be talking about Waabi's high-fidelity closed-loop simulator. Okay, and then I will go in details on that piece. All right. All right, so let's look at autonomy. And here, I'm not going to be going over details of specific methods. I'm going to be more talking about what are the things that you need, how you should be thinking about the problem, what are the things that you need to solve. Okay, just giving you a taste of some of the problems that are actually really important. All right, So I mentioned before that we want to have an end-to-end trainable full autonomy system, okay? And there is two ways that you can go around doing this. One is to be super ambitious and from day one say that I'm going to train the entire system, or you can go, piece by piece, trying to go broader and broader and broader on your scope. Okay, so this is advice for all the junior grad students out here in the, in the floor, is that don't go for the large thing. It's going to be really difficult to make progress. Try to compartmentalize your problem into something that is broader, learn about it, and expand, and expand, and expand, and at the end, you will actually capture the entire system. Okay, that's kind of the philosophy that we have done in the, in the group over the past, I would say, 10 years or so, working in self-driving. All right, so what we're going to first do is we're going to join perception and prediction, right? So 2/3 of the software stack into a single system, okay? And so the easiest way to do this is actually the, the first model that, that we developed and then put it to production actually during the Uber days. So this turns out to be very simple, but work extremely well, much better than the handcraft kind of perception prediction system. And the idea is very simple right now that all of you are excited about AI, is that you can take the raw sensor data and then have a neural network that basically performs detection, and for every one of your detections also predicts the trajectories into the future. So if you can do this, right, you can actually, just by using multitask learning, you can do joint perception and prediction. Trivial, right? Super simple network. Very simple idea. It turns out that this actually worked remarkably well. All right, so let me show you a video of, this was actually 2017, so quite a while ago. And as you can see here, was able to really detect really well all the objects of interest, track them over time that you got for free, as well as predict the trajectory into the future. Okay, our first attempts to trajectory prediction were actually pretty short in terms of the length. Here is only 1 second. Obviously, you need much longer than this for a real system. Okay. All right, so if you think about it, right, this was a very, very simple system, right? That is just a very streamlined neural net with classification for detection as well as, regression for prediction, right? So the other thing that, is important when you develop self-driving is that, we were pretty later-centric in our papers, but obviously the system always used more than one modality, and this is important in terms of reliability, in terms of safety, okay? And one of the open questions in the community was that, how did you fuse information between the different sensors? At the time, there was a lot of people, that advocate for late fusion, some people for early fusion. Our advocate was always to let the network learn, because it's going to know much better what is the right architecture than you as a human. Okay? And that's actually something that works really well, where you let the network fuse information across all the different layers, but you use the geometric properties that relate the two sensors, the images as well as the lidar, in order to help this fusion operation. Okay? So you don't forget about geometry, you use it, but you use it within learned representations. All right, so this actually worked really well as well. So, very fast, you can do inference, in a few milliseconds across, all these different sensors. And nicely, you only need annotations in the 3D lidar space, which is also something that you take, to take into account when you build real systems. And as you see here, the sensors get foggy, the lidar can get dirty. There is many of these. Maybe the lidar can fail, etc. So you need to train your system so that they are robust to any sensor failure. Okay. I'm of the opinion that it should be a single path instead of multiple paths, and then somehow decide, which subset of the system you execute at test time, which is, pretty dangerous, I would say. It gives you a false notion of safety in many ways. All right, so we can use now information across multiple sensors. We can do very simple predictions into the future in terms of, what is the most likely trajectory. But one of the things that is difficult about prediction is the fact that there can be many realizations of the future. So let's take an intersection here where we have two vehicles at the intersection. I'm not sure what happened to the second one on the left, but so there was a vehicle there before. Anyways, so since we don't necessarily know where these vehicles are going, there is many things that they can do, right? They can, this vehicle on the bottom can turn right, can actually take, take a left, and the same for the vehicle on the top, right? This is why it's an inherently multimodal problem, right? Not only also there is all these different behaviors, but also is the fact that there is different speed profiles, there is different spatial realizations, right? So it's important that we really handle the multimodality inherent to this future prediction, right? And so one of the things also that is important with prediction is that we take into account the interaction between these different agents, right? Because you don't drive independent of everybody else, right? We try to drive so that it's safe for everybody and we all advance towards our goal. And lastly, what is very important is that we need to build systems that actually work in real time. They're very, very fast. So when you're developing your methods, you should take this into account as well. All right, so in terms of modeling interactions, there has been quite a bit of work in the literature about what is the right representation also for multimodal predictions, right? Whether it is a mixture of Gaussians, right? This is something that Waymo likes. We like non-parametric representations. We like also retrieval-based methods that are actually quite interesting. But at the end of the day, when you look at the literature up to one of our papers and subsequent follow-ups, the interaction, so techniques were using an interaction model, for example, through graph neural networks. But after the interaction is propagated here, hopefully you see my mouse, basically what these systems predict is a marginal distribution for every actor, right? And all those papers are great. They show metrics, and they stop there. They never talk about how is this going to be used during planning, right? And this is why this holistic view is very important, because if, no matter how much interaction you predict, if you don't reason about this consistency between the different actors at planning time, you are back to square one, meaning that there is no interactions whatsoever, okay? So if you think about, predicting the marginal distributions for these actors, and let's say that you have n actors and k modes per actor, you end up to k to the n possible futures that the motion planner needs to handle. Right? That's going to be really complicated, right? That's going to be computationally expensive. That's going to be something that the planner is going to be very, very cautious if it needs to handle all these different things, okay? So we need to do something that is more at the scene level, which is something that is really missing in the literature. So let me put you this with pictures. So here is, we have the self-driving vehicle on the left, and then we have two actors that are part of the environment, right? And there is, let's say, 2 possibilities per actor, right? So there is a total of 4 possibilities of the entire scene, right? So it's either this might happen, right, which is pretty likely, or maybe this, which is also pretty likely. Maybe both are trying to go at the same time, right? So this doesn't seem to be like a good idea. They might end up in collision, right? So this is less likely, right? Or they can really cross paths, and you will, never see this, or almost never see this, right? So, but it's impossible to, by looking at the marginals, to have this to have low probability, because independently these 2 modes have high probability, therefore the combination will also have high probability, right? This is the reason why we need something more sophisticated. Okay, so one way that you can do something more sophisticated at the scene level is by representing what's happening with a latent variable model. Probabilistic graphical models are amazing. If you work with deep probabilistic graphical models, in my opinion, winner, winner, okay? So look at that if you haven't yet. But you can use these, distributed latent representations to basically represent everything that is going or happening in the scene. And what I'm showing you here is that I'm taking 2 values of this latent representation and then interpolating in between. And you see that with this one latent representation, you can actually model the interactions, how everybody is behaving in the scene. Okay, so now we have this ability to really couple the probability distribution of all the different actors. All right, so maybe a little bit more details of how to do this. So you do your detection, right? You have, in this case, a 2-stage detector, so you have your representations for every actor. We are going to have our favorite, graph neural networks, which is something that, we love in the lab to do, in order to capture the probability distribution of the latent variable Z given the input. And then basically the way that you perform inference is that you sample from the latent variable and then you decode with another graph neural network, and every decoding is actually the entire scene, okay? And that's the way that you have these samples that directly give you what everybody is doing at once, instead of going over the cross product of all these marginal distributions. All right, so it turns out that this actually performs extremely, extremely well. Otherwise, I will not be showing you this, right? And on the left-hand side are prediction metrics in terms of are your predictions going to collide into the future, which is not something realistic, as well as how well you predict with respect to what happened in reality, right, from some real data. And on the right-hand side is collision rate safety metrics for planning. Okay, it's very, very important for everybody working in self-driving that you try to always do system-level metrics. Okay, don't get stuck in perception or prediction. Try to make sure that your metrics are at the end of the system, and it will be mind-blowing what matters versus not. All right, and just to show you, some video. So here you can see, how, we are predicting, the different actors, and you see that typically multimodality only happens when it's necessary. For example, when you can, change lanes, or when you can, take a turn, right, or continue straight, etc. So it's a model that is very, very flexible compared to, mixture of Gaussians, for example. All right, so now we can build these complex prediction systems that model multimodality at the level of the entire scene. However, if you look at how good our system is as good as the sensor data, right? Because the vehicle can only do, react to things that it sees, right? That makes sense, right? Otherwise, we would be able to hallucinate the world. So one thing that is, that is quite restricted in that sense is that, if you look at the scene, things that are far away are going to be difficult to predict because there is very little observations, right? Whether it's camera, whether it's LiDAR, right? It's going to be a very tiny thing. And when you work in self-driving trucks, like we do at Waabi, you need to see extremely, extremely far in case there is a hazard so that you can actually stop this massive truck on time, okay? So this is a true problem. Some of the vehicles nearby, right, you're going to have a lot of observations, but there is also a lot of occlusions, right? And this is the canonical example of you're driving, say, in New York City, and there is the kid that comes out of occlusion, because the ball just ran on the street, right? So that actually happens relatively often, and there's, very little that you can do because you don't really see. So what's the alternative, or the thing that you can do in order to deal with this is that if you were to have, multiple eyes seeing the scene from different locations, you will be able to actually see through occlusions, right? And you can do this through vehicle-to-vehicle communication if you have multiple self-driving vehicles in the scene, or V2X if you have some cameras, say, at intersections or things like this. And this is an extremely exciting, I would say, area for research. All right, so now we're going to be able to see much better, okay? So what you can see here is we use simulation in order to, this is one of our, I guess, past simulators, where you can see, in different colors are different self-driving vehicles. Their observations are on the right with different colors, meaning which vehicle is seeing that observation, okay? And the idea now is that you have a distributed system across all these different vehicles, and then you want every one of these vehicles to leverage the information of vehicles nearby in order to be much safer and react better, okay? So one of the questions that you need to ask yourself is, how do I do this? Right? So what is the information that I should be transmitting in order to be able to, utilize the information by everybody, right? So probably the thing that everybody's thinking is like, I don't want to lose information, so what I would like to have is the sensor data from everybody else, right? And you work in robotics, right? You know how difficult it is to get real-time decision-making when you have your own sensors. Imagine now if you multiply that by 10 vehicles or whatever number that are seen all over the place, right? The millions of points are going to be tens of millions of points, and all the cameras. There is no way that you can process all that information in real time. Furthermore, you're going to need to have 5G and more in order to transmit all that information, right? So this is, not necessarily the best approach. On the other extreme, you can say that, well, maybe what I should do is just pass the end result of my inference process to everybody else so that they know what I'm thinking. And then based off, collectively, this small abstract representation of maybe bounding boxes, their trajectories, maybe we can combine this information to see better, right? The problem with this is that if you're wrong and you're very confident, you're going to corrupt everybody else, right? And if you're an adversary, that's pretty dangerous what you can do, right? So this is also not the best idea. However, in terms of transmission, you don't need a lot of information, right? So that, from that perspective, is good. So what we use is something different, which is that we are going to leverage the neural networks in order to learn intermediate representations that maintain all the information, but at the same time can be highly compressed, right? And this is something that you can actually learn just by adding an additional task loss, right? And basically, that's the representation we're going to send. So we need a small bandwidth. We don't need 5G. And at the same time, we haven't lost the information. And you can think of this as everybody is doing processing their sensors. So it's a distributed system. And then comes the information gathering and propagation. That's actually a pretty interesting idea from a systems perspective, right? All right, so here is my I guess set of self-driving vehicles. We are gonna, each one is processing their information, is arriving to that intermediate representation. That information is gonna be compressed. It's gonna be sent to the air, right? We're gonna receive that information from everybody else. We're gonna decompress it, and then we're gonna combine all that information with a graph neural network where every node is a self-driving vehicle in the scene. Okay, and this graph neural network is going to combine also using geometry, using time delay, right? Because you might receive later from some actors and others, right? It's going to combine all this information in a very robust manner in order to do better perception and prediction. Okay, so pretty simple idea that works remarkably well, and then you decode into your perception and prediction system. Okay, cool. All right, so it turns out that not only this works really well and you need very little bandwidth, but it grows really nicely with the size of the fleet that you have in the environment. This is what you want to see, right? That the more vehicles, once they are there, right, the more safe things become, right? And it turns out that it's pretty much linear how you can become safer and safer with utilizing vehicle-to-vehicle communication. All right, so now we have a pretty sophisticated perception and prediction system, right? We can combine multiple sensors. We can utilize map information. We can do things like vehicle-to-vehicle communication to see beyond what our eyes are showing us, right? The next thing that we're going to do is combine it with planning in an end-to-end system, okay? And I'm going to show you quickly 2.5 ways to do this, okay? Bear with me with the half. I will explain why. All right. So as always, the first thing that once you go into expanding even more, don't go to the most complicated thing. Try to think about what is the simplest way to actually get this task done. And again, we're going to go for a multitask approach. Okay. So you're going to have the LiDAR. You're going to have the maps. We are going to combine the information to do detection, prediction. And we are going to also output from our neural networks some information that we will use for planning, okay? And, I love sample-based planners. I think they are fantastic. They are so intuitive. You can learn all sorts of things, and that's the kind of planner that you're going to see today, okay? And so basically what the neural network is going to spit out is not directly the trajectory of the ego vehicle. Okay, we do this instead in a structured manner. I think it's a much more safe, robust way to do this. And basically, what it's going to spit out is a cost volume, which is non-parametric, of what is the cost for the self-driving vehicle for every location in a space in every time into the future. Okay, so that the way that we can do planning is that we're going to have a trajectory sampler. This is where we are only going to sample trajectories that are physically realizable. This is where your nice prior knowledge comes, such that we can index for every trajectory in the cost volume. We can sum those costs. This is something that is just a pool operation plus a sum in the GPU, so you can do it very, very efficiently. And then we do the arc-min of this. Okay, so you can do the sample-based planner with all this neural net mumbo-jumbo thing in a few milliseconds as well. Okay, very, very simple idea, but actually it works remarkably well. And all this you can train end-to-end with your favorite, for example, max margin loss, so that you don't need to be differential with some things, as well as for interpretability, we still use detection and prediction loss. Okay. So let me show you a video of this. You're going to see here the map. With the LiDAR point clouds. This is the output of perception and prediction, and this is my best attempt to showcase the cost volume. Color means different time into the future, and I'm only showing you the areas of very, very low cost. This is non-parametric, so every point in time and space has a value, but here is only the ones where, potentially we're going to do a maneuver, okay? And you see that, it's multimodal by definition, right? It's, looking at things like maybe I should take, a right, maybe I should queue behind, maybe I should be looking into slowing down or changing lanes because there's somebody, stepping into our lane, okay? And this is, again, a very, very useful representation for multimodal without specifying the number of modes, which is, how do you know a priori, right? Okay, so this is great, right? And this is the kind of planners or the kind of representations typically that most of you use for robotics, right? Typically you will do detection, prediction, motion planning, and then comes control. But there is an underlying problem with detection, which oftentimes people don't talk about, right? So let's assume that we have a scene like this. And in this case, we can, if the detection, so we are the self-driving vehicle on the bottom. If detection works well, then we're going to detect everybody and we're going to do the right maneuver, right? If for whatever reason some of these vehicles is under the threshold for detection and we only pass detection to the next stage, we don't see it, although there is evidence there is something there, right? And as a consequence, collision happens, right? This is mind-blowing, right? But this is what happens if you actually have a detection-based perception system in your self-driving vehicle. So we can't have something like this. We need to do something more. Okay, so one way to have a better representation than just bounding boxes, right? The problem there is the threshold that you are doing, right? This representation that is either there or is not there in the first place, right? So that's actually a dangerous maneuver, right? Instead, what we're going to do is predict spatiotemporal occupancy maps that are semantic. And this semantic can be quite sophisticated. Can be the category of the different actors, can be the intention and category of the different actors. For example, this is opposing traffic versus traffic that is not important for us, etc. And we're going to have these intermediate representations. We're going to skip detection altogether, and then we're going to pipe this to motion planning. Okay? And we will use a similar planner than before, which is sample-based planner. I told you before that I really like this type of planner, right? But now, instead of having this non-parametric all learn, we're actually going to have something that maybe is going to please some of the folks of the audience, which is more handcrafted, something that we incorporate more of the prior knowledge of what makes a good plan, okay? All right, so in terms of sampling of trajectories, we will do things where we use a sampler that is map-aware. This is the way that you can actually reduce the number of samples you need. And then in terms of, so we will sample trajectories, we will evaluate them all, we will cost them in the GPU very fast, and then we select the one with the minimum cost, and then the costs now are things like you should drive, in the lane center, right, on the driving paths, you should follow the route, you should drive comfortably, and then you should avoid occupy stuff that comes from the neural network in these spatiotemporal occupancy maps, okay? And they come with velocities, so you can do headway costs and things like this that those of you that work on planning, are familiar with. Cool, so the good thing about this is that you can train it end to end, right? You haven't given up that, the interpretability and the fact that you can, have automation. And again, it's very important that you have also a loss function in terms of the intermediate representation so that you do not remove the interpretability of your costs. Okay, and it turns out that this actually works much, much better than if you, particularly in terms of safety, than other types of approaches that use detection first, okay? Based on the intuition of what I told you before, that if, it's too low in the confidence, then you're not gonna see, and therefore you collide. So let me show you one of these representations where different colors means different semantics. And you see here that you can, and this is just the prediction into the future, okay? And I'm showing you what happened, but without updating the predictions, okay? So that you see, whether we were predicting, in terms of probability mass, the right thing versus not, okay? So it's pretty sophisticated, multimodal with semantics about the type of action, behavior of the different actors, and can handle also like small objects like pedestrians here and how the interactions are between the different actors. For example, this red blob is this car is stopping for the pedestrians to pass, okay? So that's something that, you're not giving up stuff, but at the same time, you get a much more robust representation. All right, and the half planner I want to talk is, I'm just going to give you a flavor into what else is important in planning. So if you think about, planning and the type of planners that I was showing you before, is that, they work a little bit in terms of like worst case. They are like overly cautious, meaning that you typically are going to select a full trajectory such that nothing happens into the future. And once you have multimodal distributions, you might have quite a bit of mass in terms of all the different modes, and then you're going to be, overcautious, slowing down to make sure that in the future you never hit anything, right? And then you will get people honking you as a self-driving vehicle because, you don't drive like a human that is a little bit more aggressive, right? So why is this the case, right? It's in the underlying way of you do the planning, that you actually cause the entire trajectory, and in reality, what is important to think about is that you are only going to execute the beginning of the trajectory, right? Because we are doing MPC, we are planning it every 100 milliseconds. But you're costing the entire thing, and if you do tracks, you are going to be predicting for 10 seconds, 15 seconds, really super long, right? So that's a tough problem to do. So, the next kind of generation of planning that you need to do is actually something called contingency planning, which is a beautiful idea, which is that the most intuitive way to think about this is that I don't need to commit to the entire trajectory now, right? Because I'm not going to drive 10 seconds blind, right, and then open my eyes again, right? I'm going to replan every 100 milliseconds. But what I should do is that I should plan a small trajectory such that no matter what happens afterwards, I can react appropriately. Right, and that's the concept of contingency planning that is, a beautiful concept. All right, so in this case, a very easy way to actually get contingency planning with the type of planners that I was showing you before is to now partition kind of the planning problem into, we are going to have short-term trajectories that are the ones that we are really going to execute, that we commit to, and then there is the what might happen afterwards, where in this case, this is worst case, right, in the short trajectory, but this is not the worst case. This is, there exists a way to plan such that I'm safe, okay? And that results in much safer planning, while at the same time not being, the overly cautious self-driving vehicle that everybody's honking, okay? So this is a very, a very important concept that actually works remarkably well.
Showcase our modern closed loop.
I'm actually, in the interest of time, I'm going to just go to the last bit, which I think I have maybe 10 minutes, and I will conclude with this. Cool. So, I talk a lot about autonomy, and I was trying to give you a flavor of what are the things that to think about and how you expand and expand and expand your horizon. And, we went more and more and more towards the task of driving, which is what matters. And this is very important because you can improve your perception system, but that doesn't mean that you're going to improve your system level metrics, right? So this is the disconnect that makes progress in the, very slow in the industry, okay? So now we're going to shift gears into, now we have, whatever is our beautiful autonomy system, okay? Hopefully I convince you that this end-to-end mumbo-jumbo is really the way to go. And now we're going to talk about testing, verification, validation, safety case, okay? And the use of simulation for this. All right, so let's get into it. So, despite the, how important simulation is, there has been, I would say, little emphasis in the community, in particularly the industry, into building the simulators that we need in order to truly validate, verify our systems offline, okay? And, lately there has been a bit more talk about, the simulation systems by all the different players. But when you look at, the details of the simulators, they are actually really a tool on a chain of tools that gives you some information but cannot replace driving in the real world, okay? And that's why it's problematic. So if you, and typically, every player will have multiple simulation systems. Then it's not like the simulator that can actually, they utilize. And there is, maybe I can categorize the simulators into 3 different types. The first one is, I don't know why it's called simulation in industry, but here it is, which is what we typically call log replay, which is basically you collect your logs offline, right? You're driving, whatever, then that becomes part of your data set. And then when you make changes to your software stack, you're going to replay the logs. Obviously, this is not reactive, right? Because if you actually execute, the new software stack will be different. Your sensor data will be different, but you don't have the ability to change it. You're just replaying what the other system did, right? So as a consequence, there is a mismatch, right? So this helps you catch big regressions, but it doesn't really tell you how well the system is performing, right? It's like the robot is just watching TV and then hoping that this way you're going to learn to play tennis, right? That's not going to happen. The second type of simulation systems that we see, right, is where you build a virtual simulation, and this typically is bounding boxes of vehicles or actors, right, and their trajectories, and then you test the motion planner, okay? So this is reactive in this case, right? It's typically as part of a video game, but the problem is that you're only testing one system of this complex software stack, right? So you're not gonna know whether the entire system performs well versus not. And the thing that we are seeing, these days quite a bit in academia, and this is not really used in industry, but maybe people are starting to invest a little bit into this, is using game engines to create data for training perception systems. Okay, that's something that typically I say that it's not really used because there is a big domain gap in terms of what the simulators do. Okay, so very scattered. Testing a little bit here, a little bit there, not reactive, maybe reactive, and not the whole thing, right? So that's why, what is the consequence of this? You have to drive millions and millions of miles in the real world to see what your issues are. This is not safe, it's extremely expensive, it's not reliable, and definitely is not the way that, things are gonna get worse and worse because the better the system gets, the more you need to drive to find the mistake. And you don't wanna find the mistake on the road, that's dangerous, right? So you wanna do it offline. So what we're going to do with simulator I'm going to show you is that we're going to invert this pyramid where we're going to use mostly simulation to validate, verify our systems, and then we need only a little bit of on-road. And the reason why is because we have this next generation simulation. Okay, and hopefully the sound works. Yep.
Ever think about what it really takes to drive? Probably not. We learn it, and we just do it. We'll stop. Think about it. Driving is hard. We process things quickly, react instantly. Our brains do this so well, it's mind-blowing. At Waabi, we're teaching the brain of a self-driving vehicle to do the same, but even better. This brain is virtual. Picture lines of code, like the Matrix. We call it the Waabi driver. But it still needs access to experiences to learn like us. That can't happen entirely out on the road. It would take thousands of self-driving vehicles, driving millions of miles for thousands of years, to experience everything necessary to drive safely. After all, there are many things that happen very rarely. We need another way. That's why we made Waabi World, our high-fidelity driving simulator, or simply put, the ultimate school for self-driving vehicles. Let's take a look inside. First, Waabi World reconstructs from real-life sensor data. We can automatically reconstruct objects, such as cars, SUVs, trucks, and more. It can digitally recreate reality as seen, or even modify it, to create an endless number of diverse virtual worlds. And we can do this across different sensor configurations, as though the driver were in a car, or even a truck. All automatically and at scale. We drop the Waabi driver into these simulated virtual worlds, and it can see and behave exactly as it would in the real world. Waabi World can then create traffic scenarios to test the Waabi driver. and generate all kinds of variations. We can create scenarios that mimic a calm afternoon or morning rush hour, 2-lane interstates or 5-lane freeways, all while reacting in real time to the Waabi driver's behavior to create interesting interactions. It's kind of like playing a video game, where every action has a reaction. The Waabi driver makes a choice, traffic reacts.
But unlike a video game, Waabi World can multiply and evolve scenarios infinitely. We can also evaluate how the Waabi driver performs in simulation and use AI to automatically generate challenging and realistic scenarios. Waabi World doesn't just test the driver to its limits, but also helps it learn new skills.
Initially, the novice driver has difficulty in a scenario. But over time, Waabi World can be an instructor and help the driver get better. So ultimately, the Waabi driver will learn on its own to drive safely in any vehicle, in any scenario, anywhere in the world. Never think about what it really takes to drive? At Waabi, we have. And Waabi World is our answer.
Cool. So hopefully you could hear, I guess, the video. So quickly go over, how do we do this? So the idea is that in order to really, remove the reliance on driving in the real world, is that you need to provide a simulator that is like the real world, right? That's the only way that you can replace it. So that means that it has to be immersive, meaning that the input to the software stack has to be of the same type as in the real world. So you need to do sensor simulation to simulate how the LiDAR, how the cameras, how the radar will have seen the scene. It has to be reactive, right? You need to understand the consequences of your actions and how your actions are going to influence everybody else. It has to have the diversity of the real world, and it has to be at scale of all the possibilities that might happen in the real world. Okay, so there is nothing like this out there, and Waabi World is the first instantiation of this. Okay, so I guess a little bit quickly here, since we're running out of time. So it's built on 4 core capabilities. In order to mimic the world, we actually reconstruct the world automatically. And that's the thing that you see here in the middle, where we can reconstruct in 3D with all the material properties, etc., all the different actors, and everything, and we only need to see the ones, right? Every time you see an actor, it becomes part of the simulator, part of the catalog of the things that you might use in order to create new things that you have never seen before. Then we have, sensor simulation in terms of cameras as well as LiDAR that is super, super realistic, right? Where the domain gap is extremely, extremely small. For example, for LiDAR is 0.5 when AP, where for Carla is 30%, 30 points, right? So that's the difference between why we can actually do this versus with other simulators you can't. Then you need to generate at the scale the scenarios, and then lastly, we, for this end-to-end autonomy, we can actually train the system in simulation as well, which is kind of the next thing. All right, so just to show you a couple of videos, right? So given raw sensor data from cameras and LiDAR, whatever platform, it doesn't need to be our self-driving vehicle, we can reconstruct in 3D, and we can do this at the scale. So all the different scenarios that you see. Then we can simulate in real time or near real time all the sensors. And the reason that we can do this super realistically and super fast is because we don't use game engines, we don't use physics-based simulation like that, super complicated as typically the industry is trying to do. We use a combination of physics and AI in order to do this. Okay, and what you see here is that we can actually, for example, I'm taking a log and I'm inserting fake objects in this log. Okay, that's a way that we can create safety-critical situations from just situations that happen in reality. The other thing that we can do is, what I'm going to show you here is what does the virtual world look like. So here is a log that we just collected by driving around a car, and then this is the virtual world, so automatically reconstructed so that we can simulate in this is real time. So you see that we can change the viewpoint, we can move around, we can change the frame rate, we can change the camera characteristics, so that you use every single log that you have collected, which everybody else in the industry needs to throw it out. because when you change the platform. And then we can also create, for example, different viewpoints as, we do trucks. We don't need to collect data with trucks. We can actually just change the viewpoint, right? And this is one pass of the log, and then you have camera simulation with this level of realism, where I have removed all the dynamic objects just to show you kind of the virtual world around the static piece. Okay. Then we can create scenarios, and the way that we create these scenarios is with 4 different ways. We do it programmatically so that safety engineers can actually super efficiently create test cases for specific capabilities. We also we can automatically import from logs scenarios that happen in reality, and then we can modify them so that they are reactive. We can generate traffic situations by using deep generative models that use multi-agent simulation. And then we can have adversarial way of generating these scenarios so that it's very easy to find the mistakes without requiring to create millions of simulations. Okay, this is very comprehensive set. And you saw before, sorry for that, that we can actually also learn in simulation, right? So we have an evaluator that gives you metrics for all the different components in real time, automatically, and you can use that for your reinforcement learning or other types of algorithms we are developing that you will see one day soon in order to do this much more efficient in terms of data. Okay, so it's a very, very comprehensive simulation that really enabled us to remove the need to drive millions of miles in simulation. Okay, so just to conclude is that the self-driving is going to happen. It's just a matter of building the right technology so that we can solve it at the scale. And it's something that, in particular, I will not stop until it's definitely out there in the world. So I hope that you're all, as excited as I am in terms of solving this task. We have plenty of opportunities. If you're interested in internships, full-time, etc., just let me know. Okay, thank you.
Okay, thank you so much, Raquel, for the inspiring and ambitious talk. Let's take some speakers from the left over here.
Hi, thank you so much. This is a great talk. I'm just wondering, is Waabi World able to simulate adverse environmental conditions like rain or snow or anything? And is that something that is on the roadmap? Thank you.
Yeah. So we have some level of right now of being able to simulate some of these environmental conditions. We are building next generation that is controllable. But since all the assets have material properties automatically created, etc., we can actually simulate some of these behaviors nicely. But we are, as I said, evolving into even better models for weather and sensor failures, etc. Yeah. And one thing to note, I think, is that when people see Waabi World, it's like, oh, this is a cool research project. This is our production simulation. This is what betters every PR core, every PR that the team, the engineers actually land in production. Okay, this is not just cool videos. This is actually the real thing.
Awesome. Thank you.
Thanks.
Okay, let's take the speaker on the right.
So this is kind of a future-looking question, but what information, if any, do you think needs to be communicated from the autonomous vehicle to the end user inside, about the level of autonomy or anything like that?
Yeah, so that depends on the application domain. For us, we are very focused on logistics, so driving trucks, Class 8, the big trucks. So we don't really communicate to the load anything, since even if it's cows, they're not going to understand. If you do passenger robotaxis, which is something I work 4 years at Uber, then you need to make sure that you communicate things so that the person that is or the people that are on the vehicle feel safe. Also that they can communicate with you, self-driving vehicle as well, in case something goes wrong, etc. So there is, this is not necessarily on my expertise, but there is a whole bunch of user studies into the kind of things that make sense to do, and that increase the adoption of self-driving technology.
Thank you.
All right, question on the left.
Hi, yeah, really inspiring talk. I was curious about V2VNet. It seems that if the network is continuing to change, then you would have to update the network from the entire fleet of vehicles simultaneously so that they're sharing sort of like information with each other? How might you handle that?
Yeah, so the design of B2B-Net is such that if you don't receive any messages, it's the same as the standard perception prediction system. So that's important as well, that you need safety even when you don't receive anything. The other thing is that every vehicle is just sending information to the medium, so you can decide what to do with that information and how much information you receive. And every vehicle does local updates. It's not really, it's asynchronously updating so that you don't have a centralized failure point, which is also very important for safety. So those were part of the design so that no matter what happens, you are safe. Yeah, great question.
We have someone in the dark in the auditorium up there.
Hello, can you hear me? Yeah. So I have a question on so you mentioned in the talk that you have end-to-end trainability and interpretability at the same time. And I was wondering how that translates into the development process. I.e., like if we find a failure during development that, like, say, perception is bad for cars under trees or the lane change trajectories are jerky, how would you go about solving this problem? Would it be to retrain the whole system? And if it was retraining the whole system, does that lead to other possible regressions in other parts of the system?
Yeah, great question. So I think one thing that is important in terms of the end-to-end trainability is that you are optimizing for the system-level metrics, meaning that by construction, you are not necessarily going to have, or your likelihood of having regressions is going to be much smaller. Depending on the type of failure, if this is not characterized well, for example, the simulator, you might need to, create, more scenarios, more things there. But what we do that is very different from others is that for every type of failure, we don't spin off a approach to solve that failure, but we make significant changes on the stack such that you can actually handle those failures in a more principled way. So and the reason why we can do these big step changes is because if you are in the complex software stack and you don't have the luxury, like for everything that you want to try to retune the entire system, right? Because that's, it will take you, many, many months in order to do, one thing at a time. So you end up having very, very incremental updates so that you don't have regressions, precisely for what you're saying, so that you can land your change. And that's why you are really stuck in terms of progress. So for us, thanks to the end-to-end trainability, you can do much bigger changes. Of course, there is a very, very rigorous safety testing in terms of, progression and regression tests, etc. There's a whole BMV that I didn't talk about here. Yeah.
Okay, let's take one final question here on the right.
Yeah, thanks, Raquel. So I have two questions. So the first one is, how do you simulate the reactive behavior of other traffic participants? And the second, will you release this simulator?
Great question. I'm laughing about the second piece. So in terms of the traffic participants, we have something that is important is, typically you will see in simulators that they use one type of traffic participant. And oftentimes is the same as the prediction or the motion planning system. That is very dangerous. For us, we have a zoo of traffic participants that you can choose just in a configuration in order to run your simulations, okay? And they are learned from data. They are validated from data. And then they are controllable in terms of, how sophisticated they are they distracted versus not, etc. And that's very, very important as you need to test, how will you behave in all these different conditions. So that's with respect to the traffic participants and the reactivity. And maybe one more thing that is important is for the structure testing, the other thing that we have is automation so that even if you make changes in the software stack, the test maintains the same. And this is through optimization, okay? So that, this is a very, very important piece of automation in the system. In terms of releasing the simulator, that's a great question. As probably most of you know, I love to release things to the community, like we are now in the 10-year anniversary of Kitty, which was a big effort we did in the past. Maybe the one thing, I would like this, Waabi World to be is a tool for regulators to test everybody into whether their systems are safe. And as part of the effort, maybe we release it to the community. But yeah, maybe a streamlined version of Waabi World might be released. Yeah. Thanks for your interest.
Okay, let's thank Raquel one more time.